forum, I think, maybe.
That's it, yeah.
My co-chair, Pamela Clark, Lunar Ice Cube Mission Science and Payload.
Great. Thank you. Okay, I might be stuck on the mic here. All right. So, yes, I'd like to talk about progress we've made on the Lunar Ice Cube mission, which is one of what I call the Lucky 13, the 13 prototypes that will be deployed from EM1, hopefully in 2018, maybe not 2018, but shortly thereafter. And this is basically the team. So Goddard is providing the payload. Morehead State University, under the direction of Ben Malfris, who's the PI, is providing the supporting subsystems, integrating the spacecraft, providing mission operations and ground support. They're about to become a substation for the DSN, their 21-meter antenna. And we have Vermont Technical College, which we are heavily leveraging to provide the ADA-based software, very reliable. BUSEC is providing the propulsion system. If I missed anybody, I think I got most of the people in there. And of course, I'm at JPL. I'm the science PI. The goals of this mission are primarily to provide basic information on the distribution of water, components of water, water in various forms on the lunar surface, to give information that will allow us to understand the dynamics of water and water components on the lunar surface, as we will basically look at water distribution at the same places on the surface as a function of time of day over a 6-month period. I point out this is the most operationally complex of any of the missions that are being deployed from EM1, and we are being very ambitious about this, and you'll see that as I talk about this. If we can do so, we'll provide information on other volatiles on the surface if we have sufficient signal basically generated by them. And this will provide inputs for modeling for volatiles. I'm standing on my tiptoes here. I gotta move this down a little bit. Okay. We also have technology. This mission was funded through the Next Step program. And so this is HEOMD, Advanced Exploration Systems. Very important part of this is technology milestones that are useful in the future, besides water distribution on the moon, which is a strategic knowledge gap for HEOMD. But also we are demonstrating the propulsion system, the BUSEC ion propulsion drive based on iodine, a highly miniaturized payload. This is a broadband IR spectrometer that's about 1.5 U. That includes the electronics and the microcryo cooler. That's very small. And of course we have challenges because of it. Inexpensive, radiation tolerant bus and subsystems. We're taking advantage of the NASA electronic parts and packaging work that's been done on looking at components that we should be flying and all of the electronics on board to the extent possible. Yes, innovative use of low energy trajectories. Dave Foltis group at Goddard is providing that support. The robust flight software in ADA provided by Vermont Tech, the solar panels. And I should also mention that the microcryo cooler we're using, this will be a first time for that as well. So there's a lot of groundwork that has been put in place so that we could basically develop this concept. And these are only some of the important things that have occurred over the last 10 years, the findings that have occurred that basically are a foundation for what we're doing. We had a number of missions that provided, basically not only did detection, but there were implications for example, deep impact, that there were variations as a function of time of day on the lunar surface through a series of flybys. M3 provided maps of hydroxyl and water from the work that they did on Chandrayaan. L-Cross, much more than anticipated, abundances of volatiles as a result of the impact. And a lot of other ones provided information on the presence of hydrogen near the poles, of course implying water and water ice. Also that the distribution of water as a function of temperature, but also topography as a result of shadowing, and also polar or sun or equator facing slope. There are implications that there are variations. There's a lot more work that's going on now, analyzing a lot of these data. It's still ongoing work. So the implications that there's water in various forms and bound at varying extents on the moon as a function of time of day. We hope to be able to detect it. These are, the big thing for this instrument was to basically be able to completely capture the 3-micron band, which has a lot of interesting features. I've put them in gold here on this sheet. These are water-related components of water, in various forms, and we have a lot of these features that are occurring at around 3 microns. So we basically intend to be able to, we should be able to go out to at least 3.5 or 3.6 microns. Technically, we go to 4, but of course, thermal emission increases dramatically after 3. So we expect to be able to remove the thermal emission, get enough signal-to-noise ratio to be able to go out to at least 3.5 microns. And we're looking specifically at water as a function of time of day and latitude by going back to the same real estate once during each lunar cycle to be able to see what the water abundances are, the depths associated with each of those features on those lines. But in addition, we have a great database of other kinds of information that we can tap into, including some information on, we will be there at least in part during the time that the Lunar map, which has a neutron spectrometer, and they will be impacted by solar output, so we could potentially get some information on solar output. That may be a long shot, but the other information on regolith composition, slope, regolith maturity, age, and regolith type, train type. That's all information that's in an extensive database that's been accumulated for the moon that we can basically correlate with. This is the Birch's instrument. We have an optical box which basically consists of 2 axis mirrors and adjustable field stop, which is basically still being built. It's all aluminum construction. We don't have to keep it particularly cold, although it does have its own separate radiator. And we also have a micro cryocooler that is being used to keep the detector very cold. Well, cold by our standards, 110 K. Cold enough. And quite a challenge in an instrument that's in a CubeSat, A, and B, flying in lunar orbit. And then we have electronics, detector readout electronics, that are deliberately made relatively compact. And I give a tremendous credit to our electronics engineer, Cliff Brambora, who, because this is a very important part of the effort, because electronics drives everything, the data processing, we have all the controllers for the micro cryocooler and the adjustable field stop, has really acted as systems engineer. So he's done a tremendous amount of work to basically take the lead in getting this instrument developed at Goddard, despite an extremely small budget. I should point out that it has heritage from Dennis Reuter's instrument line, which includes Ralph on New Horizons as well as OVIRS on OSIRIS-REx. It's considerably smaller and more compact. And I point out also that that neither Ralph nor OVIRS requires a micro cryocooler because they're going into the outer solar system. So our extremely small size also includes a micro cryocooler. So it's really, when you think about it, it's very small. And we need the power, basically, to drive the micro cryocooler. That's mostly, the electronics themselves don't really require a lot of power. But on a CubeSat, because everything is so closely packed together, anything that requires power means you're going to have waste heat, and that means you have to pay a lot of attention to that in thermal design. So a big part of what we have done, and this is basically true with CubeSats generally, but especially those that require an instrument that has to be operated relatively cold, is the thermal design. We've been looking at thermal design for this instrument in its context of a CubeSat for about 3 years. We actually did modeling as part of a research and development effort at Goddard before we actually proposed this. So these are some of the components. So here is the H1R Teledyne, H1RG Mercat Telluride focal plane array with the linear variable filter, a very compact way to basically do wavelength separation. And we are actually heavily leveraging spares from OSIRIS-REx. This is the concept of the adjustable iris. Linear variable filter down here. Here is our microcryocoiler, which is, we actually replaced the original microcryocoiler, which was made by Rycor, not only because of the jitter, which is considerable. The price tag was right, of course. It was, I don't know, 10 or 20K, but you know, my dad used to say, get what you pay for. And it has, one of the nice things about the AIM, other than we heavily leveraged existing relationships to get it for very little money, is that it comes with its own controller, which is called the Iris. We now have 3 things on board called Iris: the radio, the adjustable field stop, and the controller that goes with the microcryocoiler. And this basically is a schematic for where everything is located in the instrument. I'm going to skip this slide and go to this slide. So we have basically we're looking at a 10-kilometer footprint at 100 kilometers. We're in a high elliptical orbit. So by the time we get to the terminators, and when it's a nearly polar orbit, by the time we get to the terminators, we're at almost 1,000 kilometers. The original plan was to use the adjustable field stop to control the spot size on the surface, the effective footprint. But then, we discovered that basically there's a tremendous variation if you want to get features near the terminator. So we'll be basically using the adjustable field stop, where we can change the size by about a factor of 10, and combined with a change in the integration period. And we have a lot of overlap from one period to the next. So we get basically, with our integration period that we're talking about in the order of a couple of seconds, we get basically about 4 observations over 10-kilometer. So we're within the Nyquist bandwidth basically here. So we have a fair amount of flexibility. We can still maintain a relatively small footprint and change the effective integration period. And we're going to be able to do both of those to be able to basically accommodate the dynamic range that we will see as a result of the fact that we're looking from about 1 to 4 microns, and we're going very close to the terminator. The concept of operation is basically that we get deployed from EM1 along with 12 other CubeSats within hours after they deploy the Orion spacecraft that will go into an Apollo 8-like orbit around the moon. We will basically go into a low energy trajectory over a period of a number of months, about 6 months or so, which will basically line us up to get into lunar capture. The idea is to get us into lunar capture. That part of the mission is actually a relatively small part of Delta V. 2 minutes, okay. So the idea is to line ourselves up to get into lunar capture, to have a minimal delta V to go from lunar capture to our desired orbit, which is a equatorial periapsis, nearly polar, highly elliptical orbit. And we will not basically be using the propulsion system, which is a big driver on board for all the resources we use once we get into lunar capture. Or actually, lunar capture, we use it infrequently after that. So basically, the active part of the mission takes about probably about 8 months, 8 or 9 months, and then we'll have a 6-month nominal mission in orbit, in our desired orbit around the moon. And during that time, we'll basically be, once every lunar cycle, we'll be in a repeat pattern that will allow us to go over the same real estate, and in that way we can look at time of day differences and isolate them. This is a picture of the spacecraft bus with all the various pieces that I've been talking about over the last 10 minutes or so, including the JPL X-band radio, which almost all of us are carrying. And we have X-band patch antennas for communication that will support 256 kilobits per second, and we're thrilled. That took a tremendous amount of work. This is one of the big challenges of CubeSat. So what our current issues are, most of these for us have actually been solved. We're getting CubeSats are getting subsidized to do data access and archiving through various means, because we have 13 going at one time, and so we're sharing our resources, and NASA considers it worth the investment to make basically maximal use of shared resources and to minimize duplication of effort, and to look at basically the fact that we have relatively low budgets, all of us, to do this work. Volume is a chronic problem. It will never go away. I think on the day before we actually put everything in and strap everything into the deployer, we'll probably be worried about volume. This very high variation and shock because of the SLS is being taken care of, we think, by TIVAC and Planetary Systems Corporation, who are building the deployer system Large temperature range is still an issue while we're expected to basically deal with that. Not so much on the ground, but once the Orion is deployed, they really don't want to do very much, and so some of us will get it very hot, and some very cold. That's still not resolved. Radiation, not really an issue anymore. Communication, I think we're happy with that. Thermal design, that's always an issue. We still have thermal modeling to do. That's another challenge, and that's the next. That's really the next frontier in CubeSat design. It'll be load-bearing, heat-removing materials. Either that or we go to a larger size, 12U. Conclusions. So yes, we are building a payload for a 6U CubeSat that will go into lunar orbit, that will be able to look at the systematics of lunar volatiles, at least water and water ice. We will utilize the expertise MSU has in building CubeSat buses, along with the expertise that BUSEC has in propulsion systems. And this is basically a study in creating a tailored solution with a standard platform, which is basically one of the challenges of CubeSat. Any questions?
Thank you. Jack, do you mind using the mic?
I'm curious, Pam, what's the total cost, including operations?
So it varies from one CubeSat to the next on EM1. It varies quite considerably, I will say. But for us, it's about $7.75 million. Moorhead State, the development of the DSN substation, which they're looking at as a model for other universities to have, by the way, that'll be a shared resource. NASA's doing that through their program that supports the DSN. I don't know the price tag on that. But when that's available, they'll be doing this with other universities, and so that'll be a shared resource in the community. Some of the CubeSats, the range in costs on CubeSats, on these CubeSats, it ranges from about, I think probably the least is for the Simplex program that started at about 5.6 million. Although maybe some of the CubeQuest ones and STMD are less than that. I don't know. And the upper limit is about 20 million. So it's really all over the map. So we didn't really get to budget for data archiving. We're just going to give these tables with the data that basically are processed in tabular form for the spectra. But then we were told we would be submitting data to the PDS, which was not in the AO. So that's kind of when people started to say, well, it's going to be kind of hard, so you couldn't budget for it. So we will have that. That will also be subsidized, but it will be useful. What we're doing to modify or extend the capability of the PDS, for example, or the MGS system, which is a pipeline for DSN, will be useful for all future missions. So.
Any other questions? Yeah, please. Do you mind going
to a mic?
Yeah, do you happen to know the cost parameters for the Lunar HMAP and the Skyfire? I know the
well, I think that of course LunaMap was a Simplex program, $5.6 million.